Lockheed Martin is an American defense contractor that provides products to the United States and many other countries throughout the world. With over 66,000 contracts awarded in aerospace, defense, energy, space, and other new technologies, Lockheed Martin has led the way in innovation and pushed the limits of creativity and knowledge for over the past 100 years. When the need for a joint strike fighter for the United States and its allies arose, Lockheed Martin again proved that it is at the forefront of cutting-edge technology with the presentation of the F-35 Lightning II. The fighter first took flight in 2006, and Lockheed has been manufacturing and producing the jet in the United States ever since.
The problem Lockheed Martin presented our team was to create a program that would determine the amount of tools as well as toolboxes, which we will refer to as task kits, needed in circulation based off required tools and task kits needed on the floor at all time and tool calibration intervals. There are 6 separate build areas spaced throughout the mile-long production facility, requiring combined totals of over 30,000 tools and 5,000 task kits. The tools are placed in either task kits or automatic dispensing units, also known as ADUs, for accountability and storage purposes. Each tool is calibrated in the calibration lab according to its own unique calibration interval. During calibration, it will be removed from the floor. Each task kit is inspected annually, and it and all of its tools will be removed from the floor during this inspection. When a tool is removed from a task kit, the mechanic should check out the replacement tool from his build area's ADU.
Based off of Lockheed's frequent use of the simulation software Simio, our team made the decision to model the program using this software. With this in mind, we decided to use Microsoft Excel for the tool and task kit data input. Similarly, the model utilizes a tool multiplier user input that will represent the amount of tools inside the ADUs. As you can see from our Simio model when it is running, the top loop represents the annual inspection of task kits. The loop begins by populating the model with the inputted data regarding the required number of task kits needed on the production floor from the Excel document. As a task kit is taken off for its annual inspection, the model identifies whether that specific task kit's absence drops below the minimum task kit requirement for the production floor. After a preset time in the calibration lab, the task kit will be dropped back into the loop where it will continue to repeat this process annually.
Simultaneously, in the bottom loop, ADU tools are created instantly once the model begins running. As the task kits in the first loop are created, the tools inside the specific task kit are created simultaneously as well. The tools will be present on the production floor until they are being calibrated individually, being calibrated while on their task kit's annual inspection, or when they are just being inspected with the respective task kit. This can be seen visually by the color of the tool entity, red representing an unavailable tool and green representing an available tool. By recording various experiments with the ADU multiplier changing, the experiment output shows the percentage of time that each tool meets its minimum requirement on the production floor, and the recommended number of tools and task kits needed.
Through the Simio results, as well as our on-site visit to the production floor in Fort Worth, we noticed potential tool accountability issues regarding ADUs. Mechanics tend to use tools that are not checked out to them. The current ADUs run slow and more than likely need an update. Therefore, we have proposed the following recommendations. Management requiring more of a focus of mechanics actually using the ADUs, a proactive checkout of missing tools at the beginning of a mechanic's shift, and a software update to the current ADU technology. In conclusion, Lockheed Martin can now implement the simulation model we created in their current production process. Proper implementation of the model and of our previously listed recommendations will result in a more efficient workplace with better tool availability and accountability.
Before we end this video, we wanted to give a special thanks to our sponsors at Lockheed Martin: Scott Swan, Lauren Gibbons, Dalton Kohler, Ryan Skinner, our faculty advisor Dr. Banerjee, and all of our senior design technical advisors and faculty. From all of us on Team 13, thanks and gig 'em.